Okay, welcome to the 7th class meeting. Today, we are going to start the second paper, which is not authored by myself, but very important to those rest of the papers. Here, we are going to talk about the harmonic series representation and translation series representation. Just a second. So again, I need to do some control. Okay. Display, copy. So, okay, now we are continuing. So, I searched the harmonic series representation using Google search. And of course, there are other areas of scholarly society talking about harmonic series representation. But if you further confine harmonic series representation with, for example, cyclostationary random processes, then you have this correct search result. And it also provides some links where this paper you can also find. So you read this paper yourself, but I'm going to cover the key results which will be repeatedly used in the rest of the semester. So the thing is this. Suppose x of t is a second order random process. Here, the terminology second order random process often means different things, but here I adopt the definition that it has finite power for all t. So here, second order means that it has non-central second order moment well defined. Got it? And usually, second order random process sometimes mean the existence of mean process. So be careful. Some people assume that by a second order random process means that when the mean path is subtracted, the rest of the random process has finite power for all t. By the way, what's the difference between definition 1 and definition 2? In definition 2, it is assumed that you have the mean path well defined. So let me remind you the Cauchy random variable. I don't remember exact coefficient, probably pi or 1, or I do not remember. But suppose that you have a continuous random variable that is called Cauchy random variable. A is selected to make the overall integration of the density equal to 1 to make it a legitimate PDF. Then let me ask you a question. Given this Cauchy random variable, what is the mean and what is the variance? So many of you will try to plot this density function, which is obviously very similar to a bell-shaped curve. But usually people don't say this is a bell-shaped curve because the term bell-shaped is kind of shaped, reserved for what? Normal distribution or Gaussian distribution. So never say that the Cauchy distribution has bell-shaped PDF. But anyway, anybody, what is the mean of this Cauchy random variable? You are very tempted to say the mean value is 0 because it's symmetrical with respect to 0. And you are wrong, okay? The lemma you learned in your high school, even middle school, and undergraduate probability and statistics courses is that if the mean exists and the PDF has point symmetry with respect to some value mu, then mu is the mean value. So that lemma, you remember, actually assumes the existence of the mean value. Mean value is defined as what? In this case, the integration of the product x times the PDF of x. And you all know that if you plug this in here, after finding proper value of a that makes this integral equal to 1, then you have a dilemma, something like this. And what happens? Just consider some point, for example, 1. Then from here, this product decays almost proportional to 1 over x, right? And you know that 1 over x does not have a finite integration. So this part, you don't have finite integral. Similarly, that part, you don't have finite integral, even though you may have finite integral around here. So this is actually infinity. Means you don't have a well-defined mean value, even though this probability density function of the Cauchy random variable has exact symmetry at x equals 0. Got it? So the lesson is that you never assume existence if you want to be very, very precise. Okay? Second thing, which is not appearing here, is that even if you have existence, never assume the uniqueness of something. Got it? And that is a very common mistake. Even probably Blaise Pascal, the well-known mathematician of 17th century, also made in his argument about some religious game theory, actually. Anyway, never assume the uniqueness, never assume the existence when you want to be very, very precise in your argument. Anyway, so let me go back. Here, the second definition assumes the existence of the mean process or mean path of the random process x of t. Furthermore, it assumes what? The rest of the random process, after subtracting the mean path, has finite power for all t. So probably I want to say this one in my argument, but usually people say this as the definition of the second order random process. Of course, if you assume the existence of mean path and you define this as the definition of the second order random process, actually that definition is same as definition 2. Got it? Anyway, so let's say that we have a second order random process with well-defined mean path. Then x of t is cyclostationary with cycle period t means what? I've already introduced this definition. The first, its mean path denoted by mu sub x of t satisfies what? Periodicity with period same as cycle period. And second one is that your autocovariance function defined as the covariance between two random variables obtained by sampling at T1 and T2 after subtracting the mean value satisfies what? This interesting property for all T1, T2 pair in R squared. Ready? So you have the first property, periodicity with period capital T, and second, a kind of periodicity of covariance function. By the way, since these two definitions, just a second, these two definitions are, these two definitions are only in terms of the mean and covariance, first and second order moments. Some people say that this is Y-sense cyclostationarity and abbreviated as WSCS. Okay, question?
Y-sense stationary. Stationary type.
Yeah, so there is, of course, strict sense cyclostationarity. There is strict sense cyclostationarity. And if you want to define strict sense cyclostationarity, what would be a good starting point? Probably you remember strict sense stationarity, not just strict sense cyclostationarity. What was that? What was the definition of strict sense cyclostationarity? So let me remind you, x of t is strict sense stationary if what? If anybody? If. So whenever you want to define strict sense something for a random process, you have to go back to Kolmogov's approach to define a random process. And Kolmogov used what? The first order, second order, third order, fourth order, any nth order CDF or PDF or characteristic functions to handle full characterization of a random process. So first, the first order CDF is what? Does not change for the translation, for any translation of the origin. Second, if you consider second order CDF, then any translation does not give you different joint CDF, blah, blah, blah. So what does that mean? For any integer n, the nth order joint CDF of a random process is invariant under translation of the origin. So some people who do not want to talk about Kolmogov's extension theorem or existence theorem or various names you know from my graduate course of probability and random processes, sometimes this is simply put what? The statistical or probabilistical statistical property of x of t is not changing over different choice of the origin, which means t equals 0. Why? As you see here, what does this mean? Your choice of t equals 0 doesn't matter, right? The first order CDF is the same at t1 and same at t2. What is t1? Point from distance t1 in the positive direction. And t1 plus delta, you further move. And first order CDF is not a function of t1 and even delta. What does that mean? Choice of origin doesn't matter when you talk about first order CDF. In the second order CDF, you have chosen 2 points, t1 and t2. They have relative distance. It could be positive or negative, but it doesn't matter whether you choose origin here or there, because their relative difference determines their joint distribution. It holds all the same for all nth order joint CDF of a random process. By the way, the reason why I don't say PDF, because as many of you already know who studied carefully about my previous kind of prerequisite, even though I didn't put it in the syllabus, the graduate level probability and random processes, the defining function of a random variable is not PDF. PDF may not exist given a random variable, right? However, CDF always exists and unique. Also, characteristic exists and unique. So if I want to be precise, I would rather say joint CDF or joint characteristic function, not joint PDF. But as an engineer, you may just assume that whenever I say that existence of joint CDF, you may say that, okay, existence of joint PDF. It does not make much difference in engineering sense. So this is the strict sense stationarity of a random process. Then let me go back to strict sense cyclostationarity of a random process, especially continuous time we are talking about with the cycle period t, and period is usually is chosen as a positive number t. So anybody who wants to boldly define a strict sense cyclostationary random process? It would be very, very simple if we may define in this form, like it doesn't matter whether you choose time origin at any point. If that looks difficult, then what? This is the very choice of you. So you think similar to Kolmogorov. So I'm not going to write it here, but okay, let me write. Okay, let me write here. So, okay. So strict sense cyclostationary if what? Not delta for t. Got it? And not for all t, just for all x. Second, this should be capital T and just for all x1 and x2. Dot, dot, dot. Got it? Anybody? Everybody got it? So instead of using any delta, we restrict kind of invariance of our first order CDF when we translate the origin by an integer multiple of capital T. So what does that mean? If you draw a straight line, and if this is T1 and this is T1 plus capital T. You have the same first order CDF. Got it? And that first order CDF may be different from that CDF for T2 and T2 plus T, because it's no longer the stationary for all T, for all delta. It's for integer multiple of T. Similarly, now you choose 2 points and you translate by capital T. So now consider joint CDF of these 2 random variables. And this joint CDF is the same as that joint CDF when you sample at T1 plus capital T and T2 plus capital T. Not for just arbitrary delta, but for integer multiples of T. Got it? And you can further define the third, fourth, fifth, any nth order joint CDF and its invariance under translation of the origin by an integer multiple of T. So very good point. Got it? So everybody gets me? Okay. So if you have no idea about what is that Kolmogorov's extension theorem or existence theorem, I strongly recommend you to go to my homepage and find the teaching tab and find this course, WECE 574, Probability and Random Processes. And you may find Korean version and also English version. English version is a little bit messed up, but you will find the class note and you will find in the topic under stationarity, you will find Kolmogorov's theorem. Got it? And even undergraduate course, that is, I remember, 302. That's probably mathematics for electrical engineers A. And you will also find Kolmogorov's extension theorem because I usually talk about it even for undergraduate courses. Got it? So we have just defined strict sense cyclostationarity. Then another question. Then what would be the definition of strict sense cyclostationarity, similar to this definition of strict sense stationarity? Yeah, you are right. So statistical property of x of t is not changing over different choice of origin or shift of origin. A second, let me use this one. Time origin by an integer multiple of capital T. Okay. So this is for strict sense cyclostationarity, and that is for strict sense stationarity. Got it? So you may find some interesting result. It could be too much if it is called a lemma, but let me just say, a strict sense stationary random process is cyclostationary for all translation of the origin, for all t. Okay, so strict sense stationary random process is strict sense cyclostationary with any t. Got it? Similarly, you have Y sense stationary random process is Y sense cyclostationary with any t positive. Got it? So very, very good point. Anyway, today's topic is not that one, but the harmonic series representation. So let me explain. And this is very, very confusing at the first glance, but you will see the very close relation between cyclostationary random process and jointly Wisen stationary random processes. So here goes the related definition of two random processes are jointly Wisen stationary. So two random processes, let's say X and Y. So anybody, what is it? What's the definition of joint Wisen stationarity of two continuous time random processes? First, X of t is Wisen stationary. Second, Y of t is Wisen stationary. And third, their cross correlation function satisfies what? What does that mean? There exists a function and here be careful. The almost every textbook on Wisen stationarity, they are well written, but overestimate students' capability. Here, this function, r sub xy, is a two-variable function. And this one and that one are the same functions. However, this one has a single argument. So actually, this function is a different function. So it's an abuse of notation. But almost no professors point this out when they talk about Wisen stationarity, joint Wisen stationarity, and even just Wisen stationarity. So be careful. Actually, this means that since this is the different function, you may say that there exists a single variable function that is equal to the two variable function, which is cross correlation function, and the function is a function of time difference, t1 minus t2. Got it? And now let me ask you the extension of this joint Wisen stationarity of two random processes to n random processes. Anybody? Anybody? Yeah. Every random process is Wisen stationary, right? And second, wide sense usually means that you use up to what? Up to the second order moment, which means that you don't consider some triple correlation, right? And I don't know even how to define that. Okay. It's not emergency. So here it goes. X1, sorry. Yeah, X1, X2. A second. Sorry about that. Let me delete. So you choose any mth and nth random processes from capital N among capital N random processes. And what? there exists a single variable function that is equal to the two variable function for all pairs of T1 and T2. Got it? So for capital N equals 2, let's see whether this definition simplifies to that one. So here, if capital N is 2, then the first one means that x1 of t is y-sense stationary, and x2 of t is y-sense stationary. You may say that x1 is x, x2 is y, right? Then this part is covered. Second, since here y-sense stationarity means that you have taken same m and n, now here, if we want to remove redundancy, we only need to choose m and n different. For example, m equals 1, n equals 2. Then you have that one. Got it? So we have just extended the joint y-sense stationarity of two random processes to capital N joint y-sense stationarity of random processes. And you may wonder why this is related to cyclostationary random process. And here goes something you have to do if you have learned linear algebra. What would be that? Whenever you have something more than one, then put them in a vector. Got it? So here goes a vector random process. Vector valued random process of length n. So x underscore of x, let me just say x underscore. By the way, we don't say under bar, okay? Usually in the Western, they say this underscore. So x underscore x is what? Simply a vector valued random process with some n random processes. So by putting all the jointly y-sense station, for example, random process together, you may have a single vector valued random process. So as an educated person who learned linear algebra, whenever you have more than one something, put them in a vector, and you have a very, very nice compact notation. And also, you may develop something very, very interesting. So here goes the definition of a vector valued random process. Of course, here we assume continuous time. You may define discrete time vector valued random process too. Okay. Now, here goes a definition of y-sense stationarity of this vector valued random process. Who wants to boldly give me two properties? Anybody? And here, our definition, new definition of y-sense stationarity of a vector valued random process must be consistent with our previous definition of, where is y-sense stationarity? Yeah, of y-sense stationarity, yeah, which is not shown here. But anyway, got it? Of course, you may put capital N equals 1 to obtain a y-sense stationarity of a single random process. Got it? So this definition with capital N equals 1 must be consistent with that definition with capital N equals 1. Anybody? Definitely, you want to, this notation I really hate, because in LaTeX, it is not allowed to put underscore in Greek letter or something. So anyway, so here, mu sub x underscore t means that it's a vector valued mean path. Got it? So this is what? This is a constant vector for all t. That is the first requirement, right? What would be the second requirement? Think about autocorrelation function. That is what? The outer product or outer product of x of t1 vector and x of t2 vector, assuming these are complex valued random processes. If you want to define the same definition for real valued entries, then just replace this superscript h with ordinary transposition. Here, capital H is Hermitian or complex transposition. And let's say this, let's denote it by this one. Okay. Sorry about that. My son and daughter does not know I'm in class meeting. Just a second. Volume is 0, but anyway, so you see the consistency in the notation, okay? If you remove underscores, then this Hermitian transposition will become conjugation, and you have the ordinary autocorrelation function over a complex random process x, right? And here, if what? If there exists a single variable matrix valued function that is the function of time difference. Got it? So this is the Y-sense stationarity over vector valued random process. And here, if you choose each element of this mean vector, then you have what? Constant mean of each element of this vector. And what is this one? This is what? This is some n by n matrix valued function of two variables. And here, usually we say ijth entry of this matrix equals what? xi t1, xj t2, right? And we may just say x1, x2, t1, comma, t2. Got it? So your diagonal entries are related to the autocorrelation functions of each random component random process. And your off-diagonal element is related to the cross-correlation function. Got it? So you have a very compact form now by just simply putting all the jointly Y-sense stationary random processes in a single vector random process. So you have a mean process and autocorrelation matrix. Got it? Now, before we talk about the relation between joint Y-sense stationary random processes and cyclostationary random process, let's talk more about the frequency domain property of Y-sense stationary Y-sense stationary random vector valued random vector valued random process. Okay, so Y-sense stationary we have. Now anybody wants to define some spectral property of this Y-sense stationary random process. By the way, you know the famous theorem by Wiener and Khinchin. They relate the power spectral density of a general random process with its autocorrelation function. And its simplified version or corollary for Y-sense stationary random process is what? The power spectral density over Y-sense stationary random process x of t, denoted by S sub xx of f, is simply the Fourier transform of the autocorrelation function with respect to the variable tau, right? And this will be extended. And here goes the same theorem. Actually, it's corollary of the theorem. Let's consider this one. This one. And consider its Fourier transform. What is it? You have a matrix here. This is a matrix that contains these entries, right? Everybody with me? This is the autocorrelation matrix of a Y-sense stationary random vector, right? Ij's entry is the correlation between I's random process and J's random process, right? That's why you have N1's entry, this one, and 1n's entry, that one, right? Now, let's consider Fourier transform of this matrix. What would be a proper definition of the Fourier transform of a matrix valued function? Of course, entry by entry Fourier transform. Then what do you have? At least you may say what would be the diagonal entries. So Fourier transform of this 1,1 entry is what? The power spectral density of the first Y-sense stationary random process. And you may denote it by what? S sub x1, x1, f, because it's the power spectral density of the first entry. What about 1nth entry? It's the cross power spectral density between x1 and xn. What about n1th? Cross power spectral density between xn and x1. What about nth? The power spectral density of the nth random process, right? So suddenly, you may define something called matrix valued power spectral density. Of a vector random process. In this case, vector Y-sense stationary random process. Of course, you may define for general non-stationary random processes. That would be left for you to handle in probably in the midterm exam. And if you don't have the definition of power spectral density, which I already introduced, what was that? You time limit each sample path You now compute the energy spectral density. You divide the energy spectral density with the time interval. You take the ensemble average of that, and you take the limit when this length of interval tends to infinity, and it converges, then it is defined as the power spectral density of the random process, whether it is a strict sense stationary or Y sense stationary or Y sense cyclostationary, any, right? And that is the definition. And it looks too complicated, but be careful. Sometimes that definition, almost forgotten by almost every professors and students, gives you very simple result and properties of a random process. So never forget the definition. Even the modern spectral analyzers rely on that definition to plot the power spectral density. They just take the time-limited sample of the input signal, divide it into several chunks, and do FFT, and take the magnitude square, average over many chunks, and properly normalize, and show the result on your screen of the spectral analyzer or a signal analyzer. They do not rely on that famous Wiener-Khinchin theorem that relates the power spectral density with autocorrelation function. However, probably some of the manufacturers, they would compute kind of time averaged autocorrelation function, and they would do FFT instead of discrete time Fourier transform to find the power spectral density. So the definition, not only the definition, but also the Wiener-Khinchin theorem may be used in better implementing your spectral analyzer output or signal analyzer's output when it is set to show the result in the frequency domain. So remember that. Got it? Anyway, so now suddenly you are exposed to a highly advanced result, because interestingly, many of even electrical engineers' PhDs, not in control theory, but in other subjects, never know. By the way, those guys in control area, they are very knowledgeable about this one if they are doing some statistical control theory. I was shocked when I saw a book, a textbook, graduate master level textbook in control. They talk about this Y-sense stationary vector random process. And students are very well educated, but almost every students in other electrical engineering area, they just do not put these jointly Y-sense stationary random processes into a vector form and never think about this extension. That's a pity. Anyway, so you have now a very advanced knowledge. And here goes the question. Why Professor suddenly talks about vector Y-sense stationary random process when he was talking about Y-sense cyclostationary random process? That's weird, right? So here goes some hint about what's going on. So suppose you have a Y-sense cyclostationary random process x of t. And let me give you some result first. So here you have modulators. So first, x of t is downshifted in the frequency domain by capital L times 1 over t, right? You see this is the shifting frequency, right? 2 pi ft, right? This corresponds to negative f. So it's like, suppose you have the power spectrum of x, looks like that. Then what happens here? This entire power spectrum is shifted by negative L over t. By the way, this capital L is properly chosen so that your negative, this with center, negative t over L, contains the last smallest frequency content of the random process. So simply put, you may think about this case. Sorry about that. No. Just a second. Something's not correct. Just a second. This must be this one. And let me say, okay. This is zeroth, like it's shown, and negative ones. Yeah, so negative else. Okay, so one. So in this case, where your random process, Weissen's stationary random process, has maximum frequency content less than plus minus 3 over 2t, in that case, capital L equals 1. Okay? You have 3 Nyquist zones. This is zeros, or the Nyquist zone, and this is plus first, positive first, and this is negative first, and capital L equals 1 here. Got it? And you have e to the negative j 2 pi 0 over t. So actually, you don't modulate. And here you have the ideal low-pass filter with Nyquist zone as the passband. And you have else modulator. So you have here capital L modulator and low-pass filter pair, and L modulator and ideal low-pass filter pair, and 1. So you have total how many? 2L plus 1 path. Got it? And let's call this one as, very confusingly, x1. We want to say x negative 1, but anyway, you have x2L plus 1t. Got it? And put them together in a single random vector. So x of t equals x1 of t, x2L plus 1t. Got it? From here, something looks very similar to what I just told you with vector Weissen's stationary random process. Now, what's the relation between this x and that x underscore? You can easily say that x of t is simply what? Sorry, not this one. Got it? So from x vector, you can get original x of t. Am I right? Here, be careful. I didn't say yet x underscore is y sense stationary. But almost everybody of you have that implication of me. Amazingly, it turns out that this x is a y sense stationary random process. Vector valued y sense stationary random process. So actually, y sense cyclostationary random process is what? Equivalent. I'm not saying that they are the same. Okay? It's equivalent. Equivalent means something subtle. Got it? Equivalent to a vector y sense stationary random process. So from x, a y sense cyclostationary random process, you can obtain a vector y sense stationary random process. And even you can construct a y sense cyclostationary random process by using a vector y sense stationary random process. Got it? That is the result what we are going to show. So this is the result. So it's a kind of preview. Got it? So it's quite amazing. A single random process, scalar valued, is equivalent to a vector valued random process. And this single valued random process's cyclostationarity is nothing but the y sense stationarity of vector valued random process. This is very, very important. Got it? And how can we obtain the result? And answer is the harmonic series representation of a y sense stationary random process. So let's see. So we have around 15 more minutes. So where do I start? Yeah, so let's see. Let's first show that if element processes are strictly band limited to the Nyquist zone, so we assume that each entry of this vector valued random process is strictly band limited to the Nyquist zone, plus minus 1 over 2t. When we choose that capital T. Okay. If the bandwidth is some 5 kilohertz, then what can you say? It is band limited to 1 over 2t equals 5 kilohertz. Then you choose capital T based on that. Got it? And of course, depending on the number of element, you may choose L. By the way, you may have even number of y sense stationary random processes, then just include the 0 random process. A random process with 0 value for all t is jointly y sense stationary with any y sense stationary random process. Got it? So that doesn't matter much. So here we have L equals 1 to 2L plus 1 e to the negative is negative. It's very confusing. Okay. J 2 pi 2t 2L. Sorry about that. Minus L if I remember correctly. No, not correct. Yeah, let me just do this. Um, yeah, so if L equals 1, yeah, and XLT, right? So our assumption is that first we want to show that the converse or this direction. This is a Y-sense Y-sense stationary random vector. Then that is Y-sense cyclostationary with period capital T. So we are going to use this one. Got it? So here we have that nice property in the time domain. And we want to show what? First, we want to show the periodicity of the random process. Anybody? So here we plug this in here. Then what happens? We assume that each component random process is Y-sense stationary, which means that expectation of component random process is constant. So you have what? You have actually e to the negative j 2 pi l t over t dot 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 1 dot 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 e to the j 2 pi l over t t. And here, some constant vector. Am I right? Now, you multiply this row vector with column vector, then what do you have? You have a weighted sum of these entries. And what happens if you replace t with t plus capital T? The same, right? So you have the same result. Got it? So the first part is proved. If this is Y-sense stationary random vector, that has sample path, which is periodic with period capital T. Now, second, we want to show that the autocorrelation function of the random process X is what? Invariant on the translation of the origin by an integer multiple of T. So how can we do this? It's not that difficult. You just use the definition and write it first and substitute the equivalent form. So we are going to put that here. So what do we have? We have, let me simply call this one as E of t, because it's so confusing, right? So we have E of t, let me say E transpose, E Hermitian, just for consistency. E Hermitian T1 and X T1, right? And E Hermitian T2, X T2, and conjugate. Then what do we have? We have E Hermitian T1, expectation of X T1 and X conjugate T2, and we have E T2. Am I right? Now, according to our assumption, this X underscore vector is a Y-sense stationary random vector process. So what is this one? there exists Rx T1 minus T2. Now we have E Hermitian T1, E T2. Now what do we want? We want to add capital T to T1 and capital T to T2. And want to show this one. Are they the same or not? First, about this Hermitian symmetrical matrix valued function. You already have capital T canceled, so they are the same, right? Now, what about this E vector? E vector is here, and we've already seen here. Actually, this is nothing but E Hermitian T mu x equals E Hermitian T plus T mu x, because they are the same. So we are done. Got it? So we have the exclamation mark here. Got it? It's not factorial. It's correct, right? Got it? So you see the power of this vector matrix form notation? It makes everything simple. And you will see that even the authors of this paper in 1970s didn't use vector matrix notation, even though it's obvious. Why? Interestingly, even when I joined the communications kind of academia around 30 years ago, interesting thing was going on. In communication society, not many people were using matrix vector notation, even though they have finite number of something and some IJ pair, blah, blah, blah. In signal processing society, this notation was very popular. And when I became a PhD student, now the change was started. So as you see here, very old communications or even information theory paper does not put them in a matrix. Got it? So whenever you read very old papers, be careful. Sometimes you are just looking at very old style notation. And there are much better notations. Got it? Anyway, so I've just shown you that if x underscore is a y-sense stationary random process, vector valued random process, then this direction gives you a single scalar valued, possibly complex scalar valued random process is y-sense cyclostationary with period capital T used here. Here, be careful. The component random processes must be band limited to the Nyquist zone in our derivation. It can be somehow generalized, but you may have different result. Now, question then. What about the other way proof? So given a y-sense cyclostationary random process, if you transform x of t to x underscore of t, can you show x underscore of t is a vector valued y-sense stationary random process? Actually, yes, because in our derivation, we just used the if and only if equalities only. So actually, we have already proved the result. And why this is so? Because under our assumptions on the strict band limitedness and number of capital L, there is no just one side implication. If you have x of t, you get x underscore of t. If you have x underscore t, then you have x of t. So automatically you have y-sense stationarity of the vector valued random process, even though I do not precisely, carefully define and prove them. Got it? So even though the original paper in 1975 talks a lot about their derivations, actually, the derivations can be much simplified by using vector matrix notation. But still, they show this block diagram for harmonic series representation. See that? Here, they call X, Y, and they never name this as Y of t. But you see, sorry about that, low pass filter. Sorry about that, not here. So this is Y of t, and that is Y t. By the way, this part is a little bit confusing here, but it's related to actually MIMO system. So we have almost just 1 minute. So let me just simply expose you what's very, very interesting. You know that we love linear time invariant filtering over signal and random process, right? So here goes LTI filtering over a Y-sense cyclostationary random process. Are you very tempted to rewrite in this way and claim that there exists some matrix valued LTI system that gives you Y underscore, just a second, this underscore is very misleading. So let me just use kind of bold-faced. By the way, the authors never introduced the definition, but here I will use this structure as fresh vectorizer. Okay. So entire block. I sent the message. He didn't read. Okay. Let me call this as a fresh vectorizer. Got it? Here, fresh means frequency shift. And this terminology is very, very popular in signal processing. Frequency shift. Got it? So this direction, we may call it a fresh vectorizer. And that direction, the other direction, may be called fresh scalarizer. Okay? And the question is, so fresh. Question is, what is the relation between these two? Got it? So in other words, given an LTI filtering over cyclostationary random process, and you will see that the output is also cyclostationary with same period. First question is to show that when you have Y-sense cyclostationary random process and LTI filter, you have Y-sense cyclostationary random process output. That is the first thing you need to show. Second one is that this input-output relation is equivalent to something like this. Of course, you can easily see that this must be 2L plus 1 by 2L plus 1 matrix valued function, or you may say that this is a multiple input, multiple output system with 2L plus 1 inputs and 2L plus 1 outputs. So suddenly, very interestingly, single input, single output LTI system has its equivalent form in multiple input, multiple output system. Very interesting, right? Via the transform using the fresh vectorizer and scalarizer. So question is, what is the relation between these two? What would be the relation? And the answer is actually, I will give you the answer. It's a diagonal matrix valued function with this one. Here, this is the fresh vectorized version of H. So H of t is just a deterministic function. However, you can put it to the fresh vectorizer to vectorize this signal. And you have 2L plus 1 length vector valued function. Now you put each entry in the diagonal entries of this matrix. Then you have this result. Got it? Very interesting. And this gives you a lot of simplification in handling Y-sense cyclostationary random process filtered by an LTI system. Because you just convert it to a band limited, each entry of these are all band limited random processes and signals, but now you have multiple input, multiple output system. And which actually you are very familiar with, because most of the current graduate students in electrical engineering, especially systems area, they are taking what? Graduate level linear systems theory, and there they have what? Vector valued signals and random processes, even though the usually only signals part are handled. But you know a lot about some singular value decomposition of that H matrix. And some of you already know some observability and controllability related thing, and those stuff learned in graduate level linear systems theory. It's amazing, right? By the way, let me further tease you. What if H of t is not diagonal? So the question is like this. Suppose you have, now we consider kind of converse. Suppose we have vector valued signal input, vector valued signal output, but not diagonal, non-diagonal square matrix here. Then what would be equivalent linear system? It could be, it never can be nonlinear, right? Everything is linear. Linear system that relates x and y. And the answer is what? Anybody? Think about that. So I will talk about the answer on this Wednesday. Ready? So that's all for the day. Let me stop.